The Mobius function of a poset. In what follows, we will develop some powerful computation techniques for a large class of posets. This class includes all finite posets. If the reader is only interested in the finite posets, she can skip to the next two paragraphs. In those paragraphs, we discuss what other posets will belong to this class. If x, which is less than or equals to y, are elements of P, then the set of all elements Z satisfying x which is less than or equals to Z which is less than or equals to y is called the closed interval between x and y and is denoted by the closed interval between x and y. If all intervals of P are finite, then P is called locally finite. Note that this does not necessarily mean that P itself is finite. The set of all positive integers with the usual ordering provides a counterexample. A set of elements I which is a subset or equals to P is called an ideal if x is in I and y which is less than or equals to x imply that y is in I. If an ideal is generated by one element, that is I equals to the set y such that y is less than or equals to x, then I is called a principal ideal. For example, if P is equals to Bn, then the ideal of all subsets of K braces is a principal ideal, while the ideal of all subsets that have at most 4 elements is not. In some of our theorems, we will have to restrict ourselves to posets in which each principal ideal is finite. In other words, each element is larger than a finite number of elements only. Note that this is a stronger requirement than being locally finite. The poset of all integers is locally finite but has no finite principal ideals. Finally, we note that dual ideals and principal dual ideals are defined accordingly. Let int of P denote the set of all intervals of P. Definition 16.10. Let P be the locally finite poset. A locally finite poset, then the incidence algebra I of P is the set of all functions f which maps from int of P to R. Multiplication in this algebra is defined by f dot g of x and y is equals to the summations of f of xz times g of zy, summing for all x which is less than or equals to z which is less than or equals to y. This definition of multiplication may seem odd at first sight. Note, however, that this is precisely the same as matrix multiplication. Indeed, take any linear extension x1, x2, x3, and so on to xn of P, and define the n by n matrices F and G whose ij entries are f of xi, xj, and g of xi, xj. These matrices will be upper triangular. Taking their product Fg, we can see that the ij entry of this product is the summations of f of xi, xk times g of xk, xj, summing with index k starting from 1 to n, which is equals to the summations of f of xi, xk times g of xk, xj, summing with k starting from I to j, which is equals to the summations of f of xi, xk times g of xk, xj, summing for all those xk which is between xi and xj, as claimed. So, the incidence algebra of P is isomorphic to the algebra of n by n upper triangular matrices. We will alternatingly use the function terminology and the matrix terminology in our discussion. Does I of P have a unit element that is an element U so that U times F is equals to F times U which is equals to F for all F which is in I of P? The above discussion shows that it must have, as the algebra of all upper triangular matrices does have one, namely the identity matrix. The corresponding element of I of P is the function delta, satisfying delta of x, y, which is equals to 1, if x is equals to y, and the delta of xy, which is equals to 0 if x is less than y. It is straightforward to verify that indeed this function satisfies delta times f equals to f times delta, which is equals to f for all f which is in I of p. So it is indeed the unit element of I of p. The following element of I of p is also a simply defined 0, 1 function. It is surprisingly useful, however. Definition 16.11. Let P be a locally finite poset. That zeta of in I of p be defined by zeta of xy equals to 1 if x is less than or equals to y. Then zeta is called the zeta function of p. A multi-chain in a poset is a multiset of elements a1, a2, a3 until am, satisfying a1 which is less than or equals to a2, which is less than or equals to a3, which is less than or equals to am. Note that the inequalities are not strict, unlike in the definition of chains. Proposition 16.12. Let x which is less than or equals to y be elements of the locally finite poset P. Then the number of multi-chains x equals to x0, which is less than or equals to x1, which is less than or equals to x2, and so on, which is less than or equals to xk, which is equals to y, is equal to zeta to the k of xy. Proof by induction on k. If k is equals to 1, then we have zeta to the 1 of xy equals to 1 if and only if x is less than or equals to y, and the statement is true. In fact, the statement is even true if k is equals to 0. Then zeta to the 0 of xy is equals to delta of xy, which is equals to 1 if and only if x is equals to y. Now assume that the statement is true for all positive integers less than k. Each multi-chain x equals to x0, which is less than or equals to x1, which is less than or equals to x2, and so on, which is less than or equals to xk equals to y, can uniquely be decomposed to a multi-chain x equals to x0, which is less than or equals to x1, which is less than or equals to x2, and so on, which is less than or equals to xk minus 1, which is equals to z, and the two-element multi-chain z, which is less than or equals to y, where z is between the interval between x and y. Fix such a z, then our inductive hypothesis implies that the number of multi-chains x equals to x0, which is less than or equals to x1, which is less than or equals to x2, and so on, which is less than or equals to xk minus 1, is, which is equals to z, is zeta to the k minus 1 of xz, while the number of multi-chains z, which is less than or equals to y, is zeta of zy. Summing over all z, we get that the total number of multi-chains x equals to x0 less than or equals to x1 less than or equals to x2, and so on less than or equals to xk equals to y is the summations of zeta to the k minus 1 of xz times zeta of zy, summing for all z in between the interval of x and y, which is equals to zeta to the k of xy. The above proof shows that the number of elements of a multi-chain, or chain for that matter, is not always the handiest description of its size. We will sometimes use the length of the chain or multi-chain instead. The length of a chain or multi-chain is the number of its elements minus 1. For chains, this has the following intuitive justification. If we walk up in the Hasse diagram of the poset from the bottom of a chain of length k to its top, we will make k steps. Lemma 16.13. Let P be a locally finite poset. Let xy the interval, which is in int of P. Then the number of chains of length k that start at x and end in y is zeta minus delta to the k of xy. Proof is analogous of that of proposition 16.12. Does the zeta function of P have an inverse? That is, does there exist a function mu in I of p, so that zeta times mu is equals to mu times zeta, which is equals to delta. Again, resorting to our usual help, the matrix representations of the elements of I of p, we see that the answer to this question should be in the affirmative. The zeta matrix Z of p is just the n by n matrix, whose rows and columns are labeled by the n elements of p according to some linear extension of p, and Zij is equals to zeta ij. Indeed, zeta of xx is equals to 1 for all x in p. Therefore, all diagonal entries of the zeta matrix Z of p are equal to 1, so the determinant of Z is equals to 1 as Z is triangular. Hence, Z to the inverse exists, and those who remember the formula for the inverse of a matrix know that the matrix Z to the inverse will have integer entries only. It turns out that the inverse of the zeta function of p is even more important than the zeta function itself. Therefore, it has its own name. Definition 16.14. The inverse of the zeta function of p is called the Mobius function of p and is denoted by mu equals to mu p. Computing the values of mu by computing the matrix Z to the inverse of Z could be quite time-consuming. Fortunately, the triangular property of Z makes the following recursive computation possible. Theorem 16.15. Let P be a locally finite poset. Let x and y, the closed interval between x and y is an int of P. Then mu of xx is equals to 1 and mu of xy is equals to minus of the summations of mu of xz, summing for all x which is less than or equals to z which is less than y, if x is less than y. In other words, mu is the only function in I of p satisfying mu of xx equals to 1, and the summations of mu of xz summing for all z in the closed interval between x and y is equals to 0 for all x which is less than y. Proof. One readily check that mu zeta of xx is equals to mu of xx times zeta of xx equals to 1, and mu zeta of xy is equals to the summations of mu of xz times zeta of zy, summing for all z which is in the closed interval between x and y, which is equals to the summations of mu of xz summing for all z in closed interval between x and y, which is equals to 0. If x is less than y. Thus, the Mobius matrix formed from the values mu of xy is indeed the inverse of z, and the proof is complete. We used the well-known fact from linear algebra that m times z is equals to I implies that z times m is equals to I, as long as m and z are both m by m matrices. Corollary 16.16. Let P be a locally finite poset. Let the closed interval between x and y is an int of P, and let us assume that x is not equals to y. Then mu of xy is equals to the summations of mu of zy, summing for all z which is in the half open interval between x and y, where the y side is closed. Proof. This can be proved as theorem 16.15, except that we have to use the equality zm equals to I instead of the equality mz equals to I. Theorem 16.15 enables us to compute the values of mu of xy starting at mu of xx equals to 1 and going from the bottom up. Example 16.17. Figure 16.5 shows the computation of the values of mu of xy. In this example, x is chosen to be the bottom element of the poset. By definition, mu of xx is equals to 1. Therefore, we must have mu of xy equals to minus 1 for all y covering x. Then we compute all the other values from the bottom up using formula 16.1. Let us compute the value of mu of xy for some of the most frequently encountered posets. Example 16.18. Let p be the poset of all non-negative integers, and let x less than y be two distinct elements of p. Then mu of xy is equals to minus 1 if x plus y is equals to y, x plus 1 is equals to y, and the mu of xy is equals to 0 if x plus 1 is less than y. Solution. This is a straightforward by induction on y minus x. Example 16.19. Let p equals to bn and let s and t be two elements of p, that is, two subsets of n braces so that s, which is subset, equals to t. Then mu of st is equals to minus 1 to the absolute values between t minus s. Solution proof by induction on k equals to the absolute values of t minus s. If k is equals to 0, then s is equals to t, so mu of st equal to 1 by definition, and the statement is true. Now let us assume that the statement is true for all non-negative integers less than k, and let the absolute values of t minus s equals to k. Then for all natural numbers I satisfying 0, which is less than equals to I, which is less than equals to k minus 1, the interval between the set st contains k choose I elements of p that are the size of s plus I element subsets of n braces. If z is such a subset, then it follows from the induction hypothesis that mu of sz equals to minus 1 to the I. Therefore, theorem 16.15 implies that mu of st is equals to minus of the summations of mu of sz, summing for all z which is in the half-open interval where the s side is closed and the t side is open, which is equals to the minus of the summations of k choose I times minus 1 to the I, summing with index I starting from 0 to k minus 1, which is equals to minus 1 to the k. The last equality is a direct consequence of theorem 4.2. It can also be seen directly from 1 minus 1 to the k, which is equals to 0. The induction step is complete, and so our statement is proved. Example 16.20. Let p be the set of positive integers with the partial order in which x which is less than equals to y if x is a divisor of y. Then mu of xy equals to minus 1 to the k if yk is equals to p1, p2, p3 until pk, where p1, p2, p3 until pk are different primes. And mu of xy is equals to 0 if y bar k is divisible by the square of a prime number. Solution. First, note that the interval between 1 and y bar k, this closed interval, and the interval xy are isomorphic as posets. Therefore, it suffices to prove our statements in the special case when x is equals to 1. To simplify notation, we will write mu of y instead of mu of 1y. If y equals to p1, p2, p3 until pk, where the pi are different primes, then a little thought shows that the interval between the closed interval 1 and y is isomorphic to the poset bk. Indeed, a divisor of y equals to p1, p2, p3 until pk is just the product of the elements of a subset of p1, p2, p3 until pk, such a set. Therefore, mu of y is equals to minus 1 to the k as claimed. We proved the second statement by strong induction on y. If y is equals to 4, then the statement is true. Now assume that the statement is true for all positive integers smaller than y. Let p1, p2, p3 until pk be the distinct prime divisors of y. It then follows that at least one of them occurs in the prime factorization of y more than once. let us call divisor of y good if it is not divisible by the square of a prime, and let us call a divisor of y bad if it is divisible by the square of prime. Then theorem 16.15 implies that mu of y equals to minus of the summations of mu of z, summing for all z which is less than y, which is equals to minus of the summations of mu of z, summing for all z good, minus the summations of mu of z, summing for all z bad, which is minus times 0 plus 0, which is equals to 0. Indeed, the set of the good elements Z is precisely the interval 1 and P1, P2, P3 until Pk. And we know from theorem 16.15 that the summations of mu of Z summing for all Z in I is equals to 0 for any interval I. On the other hand, mu of Z equals to 0 for all bad integers Z by the induction hypothesis, so it goes without saying that the summations of mu of Z summing for all Z bad is equals to 0 as well. You could say, fine, but who cares? What is the Mobius function good for? In the following paragraphs, we will try to put our answer to this question into context. Let A0, A1, A2, and so on be a sequence of real numbers and define the sequence B1, B0, B1, B2, B3, and so on by Bn equals to the summations of AI summing with I starting from 0 to n. Then, given the numbers AI, one can certainly compute the numbers BI. Conversely, given the numbers BI, one can certainly compute the numbers AI by the formula AN equals to BN minus BN minus 1. Now let F, which maps from Bn to R, be a function defined on the subsets of n braces. And let G be a function which maps from Bn to R, be another function defined on the subsets of n braces by G of t is equals to the summations of f of s, summing for all s which is subset equals to t. Again, given the values of f, the values of g are easy to compute. Given the values of g, however, the values of f are a little bit harder to compute. We have done this in theorem 70.6, showing that f of t is equals to the summations of g of s times minus 1 to the absolute value between t minus s, and we summing for all subset s which is subset or equals to t. What was common in these two examples? In both cases, we worked in a poset. In the first case, it was the poset of all non-negative integers. A sequence is just a function that is defined on non-negative integers. In the second case, it was Bn. We defined a function by setting its value in y to be the sum of the values of another function for all elements of the poset, then that were smaller than y. Then we showed that the values of the original function can be computed from the values of the new function. The major application of the Mobius function, the Mobius inversion formula, will generalize this idea for any locally finite poset P. Theorem 16.21. Mobius inversion formula. Let P be the poset, in which each principal ideal is finite, and let F, which maps from P to R, be a function. Let G, which maps from P to R, be defined by G of y equals to the summations of f of x, summing for all x which is less than equals to y. Then f of y is equals to the summations of g of x times mu of xy, summing for all x which is less than equals to y. Proof. Let x1, x2, x3, and so on be a linear extension of P. Let f be the row vector defined by fi equals to f of xi, and let g be the row vector defined by gi equals to g of xi. Let z be the zeta matrix of P, and let M be the Mobius matrix of P. Then the equality g of y equals to the summations of f of x, summing for all x which is less than equals to y, just means that g equals to fz. Multiplying both sides by m from the right and using the fact that zm equals to I, we get gm equals to f, which is equivalent to our claim. Just as theorem 16.15. This theorem also has a dual version. Corollary 16.22. Let P be a poset in which each principal dual ideal is finite, and let F which maps from P to R be a function. Let G which maps from P to R be defined by G of Y equals to the summations of F of X summing for all X which is greater than or equals to Y. Then F of Y is equals to the summations of G of X times mu of YX summing for all X which is greater than or equals to Y. Proof. This can be proved as theorem 16.21, replacing the row vectors by column vectors and right multiplication by left multiplication. Definition 16.23. Let P and Q be two posets, then the direct product P times Q of these two posets is the poset whose elements are all the ordered pairs PQ, where P is in P and Q is in Q. Little p is in capital P, and little q is in capital Q, and in which PQ, which is less than equals to P prime Q prime, if P is less than equals to P prime and Q is less than equals to Q prime. The values of the Mobius function in a direct product poset can be computed by the following theorem. Theorem 16.24. Let us keep the notation of definition 16.23. Then mu P multiplied by Q of the pair PQ and P prime Q prime is equals to mu P of P prime times mu Q of Q prime. Proof. We note that 0 is equals to the summations of mu of PZ summing for all Z which is in the closed interval between P and P prime when P is not equals to P prime, and also 0 is equals to the summations of mu of QS where S is in the closed interval between Q and Q prime when Q is not equals to Q prime. Multiplying these formulae together, we get 0 equals to the summations of mu of PZ summing for all Z in the closed interval between P and P prime times the summations of mu of QS summing for all S which is in the closed interval between Q and Q prime. Note that we also know that mu P of P prime times mu Q of Q prime is equals to 1 if and only if P is equals to P prime and Q is equals to Q prime. Therefore, the function mu P of P prime times mu Q of Q prime is the unique function defined on int of P times Q that sums to 0 on all non-trivial intervals of P times Q and takes value 1 on all trivial intervals. That unique function is, by definition, the Mobius function of the poset P times Q, and our statement is proved. Applications of this theorem will be provided in the next section and also in the exercises.